So the last video ended on kind of an amazing note. Functions can consume other functions as arguments. And letting us do that makes it possible to easily write abstract functions. And then we can use those abstract functions to write other functions that are very short, very simple to write. That's pretty great. As I said in the last video, you can do this kind of abstraction in any language, and that's why we're covering it in this course. But it's almost never going to look as clean and simple as it does in this language, so enjoy it while you've got it. What we're going to do in this video is we're going to take the next couple of steps in the design recipe. We're going to do now the check expects and the purpose for these abstract functions. Remember, we're working through the recipe backwards, starting from the working abstract function, heading back towards the signature. I'm in parameterization v2, and I'm where I left off last time, where we had gotten the working definition of contains question mark by abstracting it out of contains UBC and contains McGill. Let's work on check expects. Well, the easiest way to get the check expects is to abstract them also from the examples. One way to do it is to take the check expects for both other functions, copy them all down. Now we're not going to use all of them, of course. Now these calls to contains UBC and contains McGill in the check expects have to be replaced with a call to contains. That's the function we're doing now. Now I'm going to end up deleting a bunch of these, but because it can be really troublesome to have a call to one of the concrete functions, I'm going to go ahead and take the time to rename all of these. And of course, there's going to have to be a string argument inserted in that position for all of these. So let's see, a base case test contains, it doesn't matter what we look for, but let's look for UBC. In empty, that's still false. And I only need one base case test, so that one will go away. Now let's look for UBC in cons McGill empty. That one produces false. Here we can look for UBC in cons UBC empty, and that one is going to produce true. And let's see, let's get rid of these other one long cases, and let's get a couple two long cases. This is, let's see, both of those are one long. So let's see, if we're looking in there and we produce true, that means we were probably looking for, let's say we were looking for UBC, and here let's also be looking for UBC, but let's have a too long case where we fail. Let's look for Toronto in that list, and there we'll produce false. Now all I did here was to just take the existing examples and work on them a bit to turn them into examples for the new function. Another thing you could have done was to generate examples for the new function kind of from scratch, from first principles. But in cases particularly where perhaps the examples are complicated, taking existing examples that work and revising them might be a better way to be sure your examples work. But both approaches would be fine. Well, let's try running these examples, make sure they do work. And they do. So now again, working backwards through the HTDF recipe, we started with the working function. Now we've done the check expects. Let's do the purpose. Well, you know, these were the two less abstract purpose statements we started out with. And oftentimes that's a good way to figure out the purpose for a more abstract function. Although sometimes it's harder to get a purpose for an abstract function. The reason we're going through the recipe backwards is that paradoxically, as we go back towards the signature, each step gets harder and harder with abstract functions. And the fundamental idea of the recipe was always to do the easiest thing first. In this case, the purpose is going to come quite easily for us. It's just going to be produce true if LOS includes what? It isn't UBC or McGill, it's S. If LOS contains S, we produce true. So now I'm done with both of those. Okay? Now I would normally do the signature, but I'm going to save all my signatures to do at the end. Okay, in video 3 of this 3-part series is when we'll do the signature. I'm going to jump down here and do the map2 case. Let's see. Let me grab some examples. This time what I'll do is I'll actually do the examples more from first principles, just so you also see that approach. It's a recursive function operating on a list. So base case test is going to come first. Check, expect, map2. Now, look, in this case, even though I'm kind of typing them from scratch, I'm still going to look at the previous concrete uses of map2. Okay? Here, map2 is being called to square numbers. Here, map2 is being called to take the square root of numbers. So those look like things that map2 can do. I'll call it with square, and the base case test empty. I get empty. I'll test that right away. It's working. Let me try another one. Map2 of square, and here we'll say list 2 and 4. Well, that's going to produce list 4 and 16. Those are both working. It's also good to have a test where we make sure that map2 uses the function we gave it. So let's say check expect map2 sqrt list 16 and 9 is going to be list, the square root of 16 is 4 and the square root of 9 is 3. Let's try that. Now you might be tempted at this point to put in some other examples. You might be tempted at this point to put in some very different examples. We'll come to that in the next video when we do signatures. What we need to do now is to go ahead and do the purpose. Now let's see. Here, I'm going to copy the 2 existing purpose statements, but they're not going to help us as much. If I just base it off of those, I might be tempted to write a purpose like produce list of square root or square of every number in lawn. And maybe that is the first purpose you write. But then you say to yourself, gee, could this function, is that all it can do? Can it be more abstract than that? If you look at the body of this function, the body of map2, it doesn't say square or square root anywhere in it. It probably can do more things than that, and maybe here you do an experiment. Check, expect, map2, I don't know. Let's take the absolute value of list 2 minus 3, 4. That would be list 2, 3, 4. It does that. So this isn't it. No. Let me show you a really good purpose statement for the abstract function map2. And before I type it, let me tell you, the thing about purpose statements for abstract functions is that it usually takes a lot of tries to get them right. This one I'm about to write, I guarantee you the first person who invented map didn't come up with this on the first try. What I'm going to write is given fun and list n0, n1, dot, dot, dot. Produce list fun of n0, fun of n1, dot, dot, dot. That seems very abstract, and it is. It seems almost mathematical. Sorry about that. But let's look at it. If we call map2 with square and list 2, 4, we get back list square of 2, that's 4, and square of 4, that's 16. If we call map2 with square root and list 16, 9, we get back list square root of 16 is 4, square root of 9 is 3. If we call map2 with ABS, the absolute value function, and 2 minus 3, 4, we get back the absolute value of 2 is 2, the absolute value of minus 3 is 3, the absolute value of 4 is 4. it is doing exactly this. Given a fun and a list of numbers, it produces the list of the result of calling fun on each number in the list. So that is a much better purpose statement for the abstract function map2. So I'm going to end this video the same way I ended the last video. Here's filter 2. I want you to do the check expects and the purpose for filter 2. And I'll see you in the next video.